Goldilocks and the Three Bears. What has this got to do with climate change? My name is Steve Turton from the College of Marine and Environmental Sciences at James Cook University. At the end of this conversation with you today, I'm hoping that I'll convince you that there is a link between Goldilocks and the Three Bears and climate change. Okay, our climate has always been variable, but now it's changing. What do we mean by that? If we look at the last 10,000 years or more, but we'll go back around, say, 10,000 years, when most of human societies have gone through their various stages of development, we can see that we've lived through a highly variable climate from year to year. We've had dry years, we've had wet years, or this could be temperature. We've had hot years, we've had cool years. So we've lived through what's called a stationary climate, and we've had a coping range. We've been able to cope in terms of our societies, our agriculture, our economies. We're now moving into what's referred to as a changing climate. We are now seeing our climate change. So in this case, it might be temperature. We're seeing our temperatures gradually, they're coming up, but we're still getting variability from year to year. So that's the take-home message here, is that you can still have a variable climate that's changing. And this is pushing us out of our comfortable range or coping range into an area where we need to be looking at adapting to a changing climate. If we don't adapt, we'll become vulnerable to the effects of this change. So the take-home message here is that we've lived for many thousands of years in what has been considered to be a stationary climate, but within a coping range because of the variability from year to year. We're now moving into a changing climate where we're starting to move out of our coping range into being increasingly vulnerable. Climate change is not new. Yes, the science of climate change is not new, and these two gentlemen certainly showed that. Their work goes back to the second half of the 19th century, and in particular Svante Arrhenius, the Swede, he predicted that if we doubled the amount of CO2 in the atmosphere, this would lead to around 5 to 6 degrees Celsius of warming. And he did this based on theory and as early as 1896. So it's not a new science at all. It's not something that's just occurred in the second half of the 20th century. It's just that we now have much better models to measure some of these sorts of things and also to predict the future. All right, greenhouse gases. We've heard a lot of talk in the media about greenhouse gases, and we also need to keep in mind that natural greenhouse gases are critical for life on Earth as well. And it's a matter of having the right balance. We have these short-lived but very potent greenhouse gases, and these include nitrous oxides, which mainly come from burning of fossil fuels, methane that mainly comes from agriculture, and also it's trapped in the earth as a natural gas. Water vapor, of course, is a greenhouse gas too. Nitrous oxides and methane are relatively short-lived. They're in the atmosphere for certainly less than a decade, or maybe up to 2 decades in the case of methane. And then, of course, the one we hear a lot about is carbon dioxide, which is a long-lived greenhouse gas. This makes it a baddie because once it's up in the atmosphere, it's there for long periods of time, potentially centuries, because it has a very different molecule structure to the other greenhouse gases. However, nitrous oxide is way more potent than carbon dioxide by volume, and so is methane. The good news is, though, they are relatively short-lived. They're not up there for long periods of time. So the real problem we have is that the most common greenhouse gas is carbon dioxide, and it is very long-lived in the atmosphere. So what is the Goldilocks effect? The idea is that we've been living on a planet that has just had the right mix of greenhouse gases circulating around in its atmosphere for at least over the last 10,000 years or so. And this has allowed us to live in a very stable climate with some variability, of course, around that. The average temperature of the planet at the moment is around 15 degrees Celsius. And if we didn't have these greenhouse gases, our average temperature would be minus 18 degrees Celsius. So clearly that would make life on this planet very difficult. However, we have to keep in mind that it's about keeping the right mix in the atmosphere, the right amount of radiation coming in from the sun, and allowing some of that long wave or heat energy to escape out to space through what are called windows in the atmosphere. We're rapidly closing up those windows or escape routes for energy by adding more greenhouse gases to the atmosphere, particularly carbon dioxide. And we only need to just realise that planet not far away from our planet is Venus. Venus is an example of a planet that has a runaway greenhouse effect. Its average surface temperatures are more than 450 degrees Celsius. Way too hot. So I think you can probably see the Goldilocks analogy now. We really want to keep things just right, and we can't afford to start playing around with the mix of gases in our atmosphere. Just to show that we are living in uncharted territory at the moment, if we go back 800,000 years, scientists can very carefully extract air bubbles trapped in ice cores in the Antarctic. These provide us with a window into the Earth's history. They show the lovely patterns of the Ice Age and interglacial cycles. Here's the last Ice Age, around 18,000 years ago. Here's the last warm period, 125,000 years ago. They can go back around 800,000 years, nearly a million years. And you can see that in all of that time, greenhouse gases have varied. They've been quite low during the glacial periods, around 180 parts per million of greenhouse gases. Sorry, in this case, carbon dioxide. And you can see they've been up to nearly 300 during some of these warmer interglacials. However, here we are in 2015, we're sitting on 400 parts per million. We've never been this high in at least the last 800,000 years or so. So we are living in uncharted territory. We also have, as well as this wonderful data set from the ice cores, we also have real measurements of carbon dioxide since 1958 from Mauna Loa in Hawaii, and we can see here this really nice upward trend, and that actually, if anything, it's getting steeper since the year 2000. And it does vary from during the summer and winter because of the effects of the deciduous forests in the northern hemisphere. So we get this annual cycle of carbon dioxide, but the black line is the average. And of course, this is a little bit dated. This is 2012. We're now up to 400 parts per million. So what influences our climate? Of course, natural factors have always driven our climate. There's nothing new in that. That's why we've had those ice age cycles in the past. But of course, the rate of change then was over thousands of years, in some cases tens of thousands of years. We're now looking at a rate of change that is within decades, within the life of a human, our climate is changing. So what drives our climate? Internal variability, and these are factors that are within the Earth itself. And probably the best known of these is the El Nino Southern Oscillation. Everybody's heard of the El Nino. The year 2015, we're currently experiencing an El Nino effect. During El Ninos, we have warm water off South America, and we have cooler than average water temperatures over northern Australia. So we tend to get lower rainfall, and they get higher rainfall and floods on the western side of South America because the water's warm. This also means that there is less cool water upwelling off South America, and therefore we tend to find El Ninos. Nearly every El Nino shows globally a warmer than average year. So El Ninos are associated with warmer than average years. La Nina is the opposite effect. In a La Nina, we've got lots of cold water upwelling off South America. During La Ninas, we in fact get below average global temperatures. And years in between, they are average. So the El Nino Southern Oscillation cycle is very important for affecting temperature and also rainfall patterns around the world. We also get a whole lot of external forcing mechanisms. Volcanoes, they produce not only a large amount of carbon dioxide, but also they produce sulfides or sulfur dioxide. And these sulfides get into the stratosphere. Here's Mount Pinatubo in the Philippines in 1991, one of the biggest eruptions of the 20th century, putting a lot of, if you like, dust and gases into the atmosphere. And after that eruption, the world actually cooled for a few years. So you get global cooling following volcanic eruptions. And volcanoes, yes, they produce CO2, but human activities produce 100 times more CO2 than volcanic eruptions. So while they're important, human effects are much, much greater. The other thing that affects our climate from year to year and decade to decade and over long periods of time is the sun, because obviously it's the main source of energy for driving our planet. And the sun goes through 11-year sunspot cycles, and they're quite important because they also affect our weather and climate on the Earth. And of course, here we have another example of a mechanism that's affecting our climate. This, of course, is the emission of greenhouse gases from industry, in this case a power station. Also, we're changing the Earth's surface, we're deforesting large areas of the planet, particularly in the tropics. This is releasing a lot of carbon dioxide into the atmosphere. That's also adding to the greenhouse effect. So what we're able to do is that if we look at all the models that are out there, and there are many models produced by different groups around the world, but observed warming is reproduced by models through hindcasting with both natural and human forcing mechanisms. So what we can do is that the modelers, they run a model which is shown as the red line, or this might be a combinational average of say 40 odd models, and they compare those with the black line, which is actual real temperature measurements, a global composite temperature set, and you can see there's a pretty good fit. For example, the models are actually picking up the Pinatubo eruption pretty well, perhaps overfitting it, but overall we get about a 90% fit between the model and observations, which is pretty good. It gives us confidence then that we can go forward and run projections into the future. What's more interesting is that we can actually separate the natural forcing from the human-induced forcing, which is coming from us producing greenhouse gases. So if we only look at solar and volcanic forcing, we get the blue line here. So if we take away the human effect, we should have had cooling over the last 50 years because of these series of eruptions in the second half of the 20th century. But instead, we've had what the observations have actually been an upward trend. Here's the 1998 El Nino, showing an exceptionally warm year with some recovery after it, then it's picked up again. So we can see here very clearly that if we take away the human effect on the climate system, we should have actually had cooling over the last 50 years. Instead, we've had warming. So this begs the question, if the sun had been active and we hadn't had those volcanic eruptions in the second half of the 20th century, would we have had more warming? And the answer is almost certainly, because it would have added to the system. So a picture of a warming world. We can see here very clearly the oceans are getting warmer. This shows us since the 1950s an increase in the amount of energy. So the oceans are taking up a lot of this energy. The lion's share is going to the oceans because they dominate our planet, and the rest is going to the atmosphere. So the oceans are getting warmer. This is clear evidence of a warming world. Our sea level is going up, and it's increased, around that 15 to 20 centimetres globally since, if you like, 1900, which is around you could say the peak of the Industrial Revolution, and continues to increase. The amount of sea ice in the Arctic in the summer is declining, and has been particularly since about the 1960s. It's pretty flat for the first half of the 20th century, just natural variability. We're now seeing a decline, and some years we get recovery, but overall there's a decline in Arctic summer sea ice extent. These are all hard evidence that humans are changing the climate of the planet. So what about our region, the Far North Queensland region? What are some of the trends? What have been some of the past trends in our climate? Look at our temperatures going back over the last 100 years or so. We've got here a measure of what's called temperature anomalies. So we take a baseline of 1996 to 2005. That forms our baseline average. We then compare years going back, and if they were cooler than that average, that's a negative anomaly, so that's below the zero. If they're warmer than that baseline, which is above the zero, we get a mark, if you like, a year above that line. So you can see that there were some warm years going back, but really there are only 3 years before the 1970s that were warmer than that baseline. And now, since the 1970s, most years, well over half, have been warmer than the baseline. So we can then fit a line to that. The orange line is the 11-year running mean. You can see it was pretty flat, and suddenly we can see we're getting an increase in average temperatures. This may not look like much, but of course it is quite significant in terms of its local effects. And you can see that our trend clearly matches the global trend, which is the dashed line. So we can see a warming trend in Far North Queensland. The other thing that is consistent with the greenhouse effect is that our nights are warming faster than our days. Again, going back to 1910, you can see that before the 1950s anyway, we were having much cooler nights on average because this is showing negative anomalies. The blue line is night temperatures, the orange line is afternoon or maximum temperatures, and you can see that our nights are warming faster than our days. But even our days we're not getting any days now that are below the zero line. They're all warmer than the average baseline figure. Rainfall is interesting for our region compared to other parts of Australia where there are clear trends of either wetting or drying. What we're finding for our region, because we've got very high natural variability and also very high rainfall with the wettest part of Australia, that very high natural variability is masking any signal. And you can see here's one of the Federation drought years. Even Far North Queensland didn't escape the Federation drought. And you can see here some of the big droughts of the 60s and the 80s and the very wet years in the 70s in Far North Queensland. And when we fit an 11-year running mean to that, there is no trend at the moment. So at this stage, our very high natural variability is masking any signal in our rainfall patterns for this region. All right, so what about the future? So climatologists and climate scientists, they run these very sophisticated supercomputer models where they try to simulate what is happening in the atmosphere. And that's what this diagram is trying to show. And they develop what are called global circulation models. And they run these as a series of grids for the whole planet. And it might take a period of weeks to run a model for a particular projection. And that projection will include things like changes in atmospheric composition, such as greenhouse gas emissions. What it's trying to do is simulate all of these things that we know happen in the atmosphere, the oceans and the land. So very complicated, and there are well over 40 of these models that are available around the world. The ones that we're using in the projections I'm showing you are based on 42 global circulation models used by the CSIRO Bureau of Meteorology in Australia. So this basically is an attempt to show you what a global circulation model is. Before we do that though, we need to keep in mind that there are lag effects in the atmosphere, and I showed you before carbon dioxide is considered a baddie because although it's not as potent by volume as methane or nitrous oxides, it's very long-lived in the atmosphere. And just to give you an example, we have here an emission graph over time. So let's say emissions have been increasing, global emissions of carbon dioxide. This is not the other gases, this is just carbon dioxide. And then emissions are due to policy that they level off, and there's no increase in emissions, but there's no decrease either. The corresponding effect of concentration of CO2, this is the amount in parts per million in the atmosphere, continues to increase despite the fact that emissions have leveled off, purely because carbon dioxide is very long-lived. Once it's in the atmosphere, it's potentially there for centuries. So that means that while this policy might look good, it's actually not reducing concentrations. They continue to go up. In the second graph, we've got a model over time where emissions of carbon dioxide have increased, policies kicked in, and there's been a rapid decline in emissions of CO2 over time. And this is the corresponding concentration graph. Rather than going down, it merely levels off. So you're still buying into climate change into the future, even if you bring emissions down very sharply, as shown in this graph. And this is the problem we have with carbon dioxide, is that we're actually going to be subjecting future generations to future warming, even if we do bring emissions down in our time. We're actually projecting into the future here. Which takes us to what the IPCC do, the Intergovernmental Panel on Climate Change. I want you not to worry too much about the dashed lines because they're from the 4th assessment report. We're now dealing with the 5th assessment report that was published in 2013, so that's the most recent. we have these emission scenarios, these RCPs, are these representative concentration pathways. The red line is an assumption that we have business as usual. We continue with the current trajectory into the future of high emissions of, this is not just carbon dioxide, but it would also include those other greenhouse gases. But CO2 is the dominant one here. So the red line is business as usual. We're currently sitting on about 400 parts per million. With a continuation of high emissions, we could be well over 900 parts per million by the year 2100. That obviously is going to be catastrophic for the planet. We also have here the green line is the RCP6, and this is assuming a more modest or medium sort of trajectory into the future. That's still putting us over 600, nearly 700 parts per million. And the blue line is a low emission scenario. Even that is still going to put us over 500 parts per million. So the ones that I want you to focus on here are the RCP 8.5, the red line, the high emission scenario, and the RCP 4.5, which is the blue line, is the low emission scenario. And what are some of the projections for Far North Queensland? The one on the left here is for the low emission scenario into the future, and the average, just focus on the average line here, and you can see that even with a low emission scenario, we're still going to have warming in the region of around 2 degrees of warming, because we're buying into that because of that long-term effect of carbon dioxide. For the high emission scenario, though, we're potentially getting over 3 degrees of warming by the year 2090. So that's quite a difference. So clearly, if we bring emissions down, we'll have less warming, but we're buying into some warming regardless of what we do with emissions. But clearly a low emission future would be better. So what are some of the projections for our region? Okay, very high confidence for increases in average, maximum and minimum temperatures. Very high confidence means that it's over 95% confidence. There's very high confidence that we're going to have more hot days. These are days over 35. There's very high confidence that sea level will continue to increase, and that there will be the effects of extreme sea level events, mainly driven by tropical cyclones, will also continue to increase. There's high confidence, which is over 90%, we're going to see increasing evapotranspiration, which means more evaporation loss from our reservoirs and dams. Our vegetations are going to be subjected to more transpirational loss, therefore more stresses associated with higher temperatures. We could have high confidence that we're going to have more extreme rainfall events when they do occur. There's medium confidence, which is around 65% or more, that we're going to have less frequent but more intense tropical cyclones. What's more concerning there is the more intense tropical cyclones. There's quite low confidence, this is sort of 50-50 in a way, whether we're going to see any changes in rainfall. I think it's because we're dealing with a very high natural variability in our rainfall, but at this stage the models are not really showing drying or wetting with rainfall overall in terms of the average amount of rainfall or total amount of rainfall. But what's important though is more extreme rainfall events when they do occur, but the flip side of that is more extreme droughts when they do occur as well. So here are some figures for our region for average temperatures, just using that baseline 1986 to 2005. We can see here, with obviously the higher the emissions, the more warming we're going to get, up to nearly 3 degrees by 2090 with a high emission scenario. Days over 35, using 1995 as our reference, when they were averaged 3 days a year over 35. We could be looking at, with a high emission scenario, over 48 days a year over 35. That's a very different Far North Queensland to what we currently live in at the moment. And even with low emissions, still 11 days a year over 35. Sea level rise, again, emissions are going to be critical here. The higher the emissions, the more the sea level rise. So up to 60 centimetres, but as low as 40 centimetres with a low emission scenario. So the message is that even with low emissions, we still have to be adapting to a changing climate. Extreme rainfall days. Clearly, even with low emissions, we're going to have more extreme rainfall days, but up to nearly 20% increase, 17% here if we look at a high emissions scenario. When it comes to total rainfall, though, this is where the models are pretty split. Some models show a wetting trend, some show a drying trend. The average, though, overall is no real patterns. What I'm not showing you is seasonality, but what the models are showing is, for our region, our dry seasons are going to be drier and longer. Our wet seasons potentially wetter. So we're going to have to cope with very wet wets in some years and dry dries in some years as well. That has a whole lot of implications for our agriculture and for our ecosystems that we'll be needing to think about. So what can we do? Well, there's a few things we can do. What we will have to do is prepare and adapt to the current weather risk and the near-term climate change. So be prepared, think about adaptation. The other thing that we can do, and we can all play a role in this, is reduce our greenhouse gas emissions, because that will be the key to mitigating some of those effects of climate change that I've been talking about. Rule is that bring emissions down, we still buy into climate change, but it won't be as bad as it will be if we have high emissions. And that's my talk. Thank you very much.